Welcome to lecture 4, and as usually we will start with a very brief revision of what we learned in the last lecture. So in the last lecture we started to understand the addition of bromine to an alkene, and we saw that this reaction is regioselective and an overall anti-addition. Moreover, both the bromonium ion as well as the dibromide product are racemates. And then we learned that we can selectively produce the Markovnikov product if we use an unsymmetrical alkene for the hydration reaction in acidic conditions. And conversely, we saw that if we want to produce the anti-Markovnikov product, which is the primary alcohol, we need to do several reaction steps. And these steps were, first of all, the hydroboration of the alkene. Then we did further hydroboration steps in order to end up with the trialkylborane. Subsequently, we did oxidation to produce the trialkylborate, and this reaction had to be under basic conditions. Afterwards, we did the hydrolysis of the trialkylborate, and then we formed 3 equivalents of alcohols, and this reaction was again required to be performed in basic conditions. So this is what we learned so far. Today we want to have a closer look on the reaction between peroxycarboxylic acids with alkenes, and this type of reaction is also called epoxidation reaction. And before we can start with the reaction mechanism, we need to make sure that we understand what is a peroxycarboxylic acid. And characteristic for this peroxycarboxylic acid is the oxygen atom between the carbonyl and the hydroxide group. So we talk about this oxygen atom here. So this is the main structural unit, and the R group here is not important for the structural unit of a peroxycarboxylic acid. And an epoxide is then this 3-membered ring where we have 2 carbon atoms which are both connected to an oxygen. And a peroxycarboxylic acid reacts with an alkyne by donating an oxygen atom to the carbon-carbon double bond to form an epoxide in an electrophilic reaction. And you can imagine there are plenty of different peroxycarboxylic acids, and a prominent candidate is this molecule here. It is called beta-chloroperoxybenzoic acid, and you can directly see the important structural unit here. We have this carbonyl group connected to an oxygen, and then this oxygen is again connected to a hydroxide group. And here we have the R substituent. And this metachloroperoxybenzoic acid is often used because it is easy to handle and it's a solid which can just be stored in a fridge. If we now want to understand the reaction mechanism, we will start with bringing the peroxycarboxylic acid close to the alkene, and here we start with a transalkene. And already from all these arrows here, you can see that we talk about a concerted addition reaction. So let's start. We have the oxygen bond here, and the oxygen atom of the hydroxide group is now partially positive charged. The reason for this is that we have a very strong electron withdrawing effect of this substituent here. That means we get a partial positive charge on this oxygen atom. And hence, this oxygen atom acts as electrophile by accepting a pair of electrons from the carbon-carbon double bond. And as we see, this is a concerted reaction. That means we will move the electron pair from the carbon-carbon double bond towards this positively charged oxygen atom. Then this very weak oxygen-oxygen bond will break, and the electron pair will move towards the carbonyl group, and at the same time the proton will be abstracted from the hydroxide group. And that's why we have all these arrows. That means all these movements happen at the same time. And then we end up with this trans-epoxide and also with this acid. And what is now also important, if you have a look on this concerted addition reaction, you can directly see that as all steps proceed at the same time, there is no chance for the carbon-carbon bond to rotate. That means the epoxide retains the configuration of the alkene, which was our starting material. So if we start with a trans-alkene, we will end up with a trans-epoxide. So we can say that this reaction is stereospecific. And of course, we can also obtain a cis-epoxide. And therefore, the only thing what we change is to start with a cis-alkene in order to produce the cis-epoxide. And what is now important? The peroxycarboxylic acid can approach from either side of the carbon-carbon bond equally well. Hence, the epoxide is always formed as racemate. So what should we remember? We have a stereospecific epoxidation reaction taking place.